Okay, so this evening we're going to be looking at belt and chain drives, which is Module 7. Actually, specifically starting with belt drives this evening and then chain drives the next time we get together. If we look at Module 7 learning plan, you will notice that we are going to be focusing on Chapter 11. So just one chapter here, but it does divide it into two sections. So we'll be, like I said, hitting belts tonight and then chains the next time we're together. I will be recording and uploading my session recordings here in that folder, and then we'll notice that we do have, just like we always do, practice problems and an assignment. So this evening, we're going to be looking at the first couple practice problems, and then the next time we're together, we'll be doing the last one. Now, the sentences that I want you to complete are a couple things here. Number one, I want you to, after we're done with the information on Wednesday, let me know two things that you feel that you learned that were, important, that stand out. But then instead of telling me what you feel you need extra practice on, I changed it up a little bit where I want you to describe a place or an application where you see a belt drive. Okay. And then the same thing for a chain drive. The only exception that you cannot list for a chain drive is going to be a bicycle. Okay. I'm pretty sure we all know that application. I want you to look beyond that. Okay. So once we go over things, I think you'll be able to, kind of think of other ones or spot other ones. So that's going to be what I want you to answer for this one. And then as far as our assignment, half of the problems are going to be belt drives and half of them are going to be chain drives. So we'll kind of look at that at the end of this evening, how far you can go with that assignment if you wanted to get started on it. So let's go over to our learning plan and we're going to open up our PowerPoint presentation. And as I said, this is going to be chapter 11 in your book, which starts on page 302. So objectives here for this particular chapter are really going to be looking first of all at belt drives, as I said. So this evening we're going to be focusing on just that type of a drive. So really looking at advantages, disadvantages of belt drives, looking at different types of belts that we can apply, looking at the kinematics and the relationships of those belt drives, and then we'll change gears over to chain drives and kind of do the very same things the next time we're together pertaining to chain drives. So starting off looking at belts and chains in general, belts and chains are used to transfer power between rotating shafts. We can make that very same statement for gear drives. And we're going to find that as we talk about belt and chain drives, we're going to be seeing some of these relationships kind of pop up again. Okay. Belt and chain drives, they offer flexibility of efficiency of operation, but most importantly, we can change our center distance, whether they're closer together or further apart, more so than gears. Gears, we have to have them up against each other, engaging with one another. So we have set center distances based on the size of gears that we have. Where with belt and chain drives, we're going to find out that when if it's the belt running on a sheave or if it's a chain running on a sprocket, we can actually move those center distances apart and we can accommodate more custom, placements of those elements. Gears become impractical, especially when those center distances start to become large. Okay, we would have to create chains or trains of gears in order to accomplish larger center distances, and now we're adding parts unnecessarily. So belts and chains become a nice option, especially for that type of application. Bicycle chain drive. So I start here only because this ends up being an application that most everybody can relate to. Basically, a bicycle chain drive is going to be a chain mechanism that transfers that motion and forces of the rotating pedal assembly from where you are at on the front to the back. Okay. The velocity ratio of that chain can be readily altered by changing gears, as we say. And there's a lever up on your handlebars that then moves the chain back and forth so that it is going to be placed onto the appropriate sprockets for the chain to drive on. So changing those velocity ratios, help to make it easier or harder to pedal depending on what you're trying to accomplish. Now, we talk about belts and chain drives as being flexible connectors, and they're referred to that Mostly because, as I said earlier, we can change that center distance readily. So belts and chain drives kinematics are also going to be exactly the same, as we're going to find out that we also experienced back in gears. So when we start looking at velocity ratios, for instance, some of those relationships are going to look and sound familiar to us. So let's start off with belt drives. Okay. So belts in general, or belts as we start to look at these in section 11.2, which is also on that first page of the chapter 302, they are used to transmit rotational motion and torque from one shaft to another in a smooth, quiet, and inexpensive way. First of all, they are always going to be low cost because belts, we're going to find out, are readily available, not only because they're mass produced, but the materials that they're used to make are readily available too. So we've got rubber and fabric and steel, which aren't hard to come by, and they're relatively inexpensive to manufacture and put together. As we said earlier, we have that flexibility of positioning that center distance wherever we need it to be, whether it's further apart or closer together. Another clear advantage of belts is that it runs smoothly and quietly. When we have fabric going over a metal shiv, there's almost no sound. Okay. So that's a really big advantage, especially in applications like automotive, where we don't want to hear the movement of the mechanical parts that are, under the hood. So if we can minimize that with belts, that's advantageous. Additionally, there is no lubrication that we have to apply. So we don't have to try to get oil and grease to an area so that it's going to last longer. If we look at a belt, as far as any maintenance on it, we usually can tell if it needs to be replaced or not. So by maybe cracking or fraying or something like that. Hopefully it doesn't go too far and actually breaks. But there is no intermittent maintenance that we have to do on it, specifically lubrication, like we would have to for gears and chains. Easy to assemble and install as well as repair. Like I said, little to almost no maintenance. And then it also absorbs shock because it has that ability with the materials that it's made out of. It can actually stretch a little bit if it's overloaded. Okay. Now, as we look at belts, what I want to do is, I just want to peek ahead here for just a little bit. Yeah, I want to go here. I want to look first at figure 11.1 on page 303. And at the top here, in that first left-hand column, you're going to notice that we're seeing a cross section of some very common types of belts. Now, the belts that we're going to be using for our exercises and for the assignments that we have is we're going to be dealing with just kind of a regular V belt, okay? And the V belt gets its name by, if you can see its cross section here, is a V shape, okay? It is going to sit down into what we call a shiv, and it is going to have a matching V cross section as well, and we can see that down here. Now, I happen to have some belts here in the room, and I'm going to do my best to put them underneath our camera. So kind of that first kind of basic, here a little bit higher. The first type of, this is a shiv, and a shiv is going to be what the belt actually fits over the top of. So you're going to notice that, hope you can see it, there is a V cross section in here. And then our belt has that same cross section and fits right into the groove here. So when it's operating, that belt is going to fit over the top. I know it's not that great to see here because my shiv is kind of large, but then we are going to have, I'm going to turn the page here because we'll be referencing this quite a bit. At the bottom of page 304, this is where we see an actual kind of generic belt drive and what it actually looks like. So a complete belt drive is going to be the combination of two shivs, okay? So the shivs are going to be what the belt rides on and fits over the top of. And then we're also going to specify a belt that fits down into that groove and how long that belt is going to be to maintain whatever center distance it is that we're going to be needing for our design. Okay, so 2 sprockets minimum and a belt is going to make up a belt drive. Okay, now In the case, like I said, kind of going back over here, in the case of the V-belt, that V-belt, as we kind of can see with the physical part here, fits down into the groove of our shiv, okay? And so what that means is when I pick my belt, I have to get the right shiv for that belt to fit down into. If it's wider or smaller, obviously it's not going to operate the way that it's supposed to. Okay. Now we can get single V belts or we can get them with multiple V belts. We can get them in 2s, 3s, 4s, 5s, and I think 6s and 8s. And then after that, it becomes kind of sparse. Okay. I have an example of kind of a V belt that has multiple grooves. I think you can kind of see it here if you're online. But then you would have to match up a shiv, obviously, that would fit and have that same profile as the number of grooves that you have in your V belt. The next one we have here is a cogged belt. The cogged belt, you're going to notice, I don't have one here in the classroom, but it's got these little notches out of it, not to fit over the top of any type of a toothed wheel, but this allows a bigger, chunkier belt to make a radius. Okay, so it takes a little bit of material out of there in order to do that. And then lastly, the kind that we have here is called a timing belt. A timing belt kind of works a little bit more like a chain. I think it's like the combination of a chain and a gear. So for instance, look first at the shiv. This is a timing belt shiv. And instead of having that groove, smooth groove that it fits down into, there are teeth on that perimeter. Okay. And then what happens is our timing belt has teeth that are the same profile as the inside of our shiv. And then now what we have is it's going to fit down in there and it's going to intentionally be on those teeth. So you have a more positive way, if you would, of pulling the belt around. Now, a couple things about a timing belt that are different is that because it has those teeth that it's going to fit down into, it's not going to slip as readily and easily when it's overloaded, which is a clear advantage of a V-belt. Meaning, if my V-belt drive gets overloaded, what can happen is because this is a smooth groove around the entire shiv, that belt is going to slip at some point. And what that does is it saves down the way, downstream, if you would, components that would otherwise be very expensive to replace. Okay. So sometimes we intentionally use a V-belt that's smooth like this, that has a V shape, so we can get that slipping when it gets overloaded. When we have a timing belt, we're going to have to kind of deal with that kind of not overloading, not slipping when it overloads, just because of the nature of the teeth then on that belt. Okay. All right. So materials that we have on V-belts, as I mentioned earlier, many of them are going to be rubberized fabric, rubberized cord, reinforced plastic, leather, and then sometimes they even have like metal strands that are going through them to reinforce them as well. So a lot of different combinations, almost like a composite, if you would, to put them together. The types we already talked about and then found on that page 303. Now the shivs are going to be the wheels that are connected to shafts that the belts are going to fit over the top of, okay? They're going to be classified by their pitch diameter, and we're going to have certain sizes that are commercially available for the different size belts that we can put on them. So here is a cross-section of a shiv, okay? And the pitch diameter you're going to notice is not the top of the shiv or at the very bottom root where that V-belt sits down in. It's kind of in between, sort of like a pitch diameter on a gear. And this is where we're going to see most of the force and the torque be pushed through that belt. Okay, so it's going to be classified by the pitch diameter. So again, it's going to be this kind of imaginary diameter, not really imaginary, but it's the effective diameter of that shiv. When it connects to the shaft, it's going to be going through the bore here, and that's why we normally have a hub, so that we get a little bit more area that it's going to ride on the shaft. Now, these pitch diameters are going to be standard sizes based on the size of the belt that we're going to run. Now, for V belts, if we have a manufacturer, they're going to minimally have these three sizes of V belts, okay? So they're going to have 3 Vs, 5 Vs, and 8 Vs. We're going to find out on another chart that's coming up how to size appropriately on each one of those. As we look at their sizes, 3 Vs are going to be the smallest of the three. 5s are the middle, and then 8 Vs are going to be the largest. As you can imagine, as we go from small to large, we get, smaller, less volatile types of applications up to the more, chunky, bigger types of forces and torques that we're putting through. Once we determine what is the size of belt that we're going to be using, on each one of these columns, this is going to list the standard pitch diameters for the shivs that are available in that size. So here we have 3 V belts. Notice that we have a number of sizes here, and this is in inches, 2.2, 2.3, but then it jumps to 2.5, 2.6, jumps again to 2.8. So what we need to do is, working off of a standard list of pitch diameters for shivs, this is how we're going to pick the diameters for the drives that we're going to be specifying, okay? So when we say commercially available, they have to be on this list. Now, when you're out in industry, there are manufacturers of V-belt drives. So they're going to have these 3 sizes for sure, minimally, but most often each one of your manufacturers is going to also have an expanded product line to be a little bit more specific to different types of applications or expectations that you might have out in the field. So then what's going to happen is that manufacturer is going to have a process that you follow. When you take machine design elements next term with Ryan, he's going to have you pull out open, in a lot of cases, actual product catalogs online, and then you're going to specify using their process. Okay. So like I said, they're going to have these minimum, but they're going to have some more sizes kind of in between or different types that you can choose from. And then you're going to size to their application. We're going to find that the charts that we have here, although they are standard sizes, when you're out in industry, you're not going to pull out your kinematics book. You're going to go directly to the manufacturer's catalog. Now, I think for some reasons, it's obvious why we would want to do that. Tell me why you think we would want to always use a manufacturer's process for sizing elements that we're going to incorporate into our design. And anybody can participate. So if you're virtual and you want to put it in the chat or audibly, or for those in the room. So why do we want to use and be specific on a manufacturer's process for sizing their element like a V-belt?
So you don't have to pay to have a custom belt made?
Yep, you don't have to pay for custom builds, and you're going off of something that's available, right? Readily available. Yep. Tyler, what was your idea? Oh, that was okay. All right. Yep. So that it's off the shelf, if you would, like we can get it right away. I have one of these guys. You've probably gone to like an automotive store or the hardware store, and they have like these belts hanging, right? If I can get a belt like this and just go to Ace Hardware or to Napa, way easier and cheaper because they're mass produced, right? So yes, being able to get their standard sizes. Perfect. What's another reason why we want to use their manufacturer's process? Their data is going to be specific to their product line, right? So if it's saying that it's going to last this long for this many RPMs, it's going to carry this much force or torque, we should be able to plan on that. Yes. What else? I'm thinking further down the life cycle of our belt drive. Let's say we get it out in the field and we're expecting it to last about 3 years. Okay. And a month in, all of a sudden it breaks. Why do we want to be sure that we use the manufacturer's process for sizing that belt for our application?
Well, much easier to get a replacement or just to figure out what went wrong.
Like a warranty, right? It might come underneath a warranty where they have to then stand behind that. What if somebody gets hurt or dies? Hope not, but it can happen, right? Then what? Why would we want to use manufacturer's data for that?
So you can sue them.
Well, so that the liability is shift off of us, right? Because if we don't use manufacturer's data and somebody does get hurt, the company and or you could be sued and be liable for that. So we always want to, when you are incorporating any third party or vendor catalog components, bearings, belts, chains, gears, you want to use their specific data for how you're sizing. We use our textbooks a lot just for ease of having the data available. And yes, these are standard sizes, but you want to go to them specifically. David.
Obvious. Belts is the more standard part obsolescence.
Oh yeah, obsolete parts. Yeah, you don't want to be specifying things that aren't going to be available, right? That's why, and I've learned my lesson. Well, I learned my lesson more at my previous college because I had paper catalogs sitting on my shelves for quite a long time. And then something went obsolete. And when the students went from the catalog, the paper catalog, to online to download the file, all of a sudden it wasn't there because now it's not available anymore. So you always want to have current information so that you don't exactly, yeah, redo the whole project because so yeah, it is really essential that you're making sure that you've got current and non-obsolete parts. Excellent. Any other input on that subject? Okay. So again, I don't want to minimize the validity of what we're doing here. You're going to do very similar processes, but you want to be specific to any vendor that you would be working with out in industry. Okay. All right. Good, good, good. All right. V-belts. So when we have an application, we need to determine what is the size of the V-belt that we're going to be choosing. So like we said, those three standard sizes, 3V, 5V, or 8V. And we have an application like, okay, where do we start? We don't want to just like randomly pick something and go with it. We want to be able to have a good place to start. And that good place to start is going to be at the top of page 304. This is figure 11.4. And you're going to notice that on this chart, there are kind of three zones, one for 3V, 5V, and then one for 8V. To select it, what we want to do is we want to look at the horizontal and the vertical axes here. And first of all, we need to determine what is the design horsepower, the horsepower that we're going to be pushing through this application. And that'll usually be given in the description of the problem that you're going to be looking at. If you're out in industry, you'll know. You'll look at the rating on, for instance, a gas engine as an input or an electric motor that you're going to be using as an input, and you'll know how much horsepower that you're dealing with, okay? So you'll pick your horsepower along that horizontal axis. Then what you're going to do is you're going to match it up with the RPMs of the faster shaft, okay? The faster shaft. So what that means is as we look at our application of a drive, just like with gears, the smaller gear, the pinion, was on the faster shaft, okay? And it engaged with the larger gear in the set, which was called the gear, pinion and gear, that was going to be going slower. We see that there is a smaller sheave. This sheave is going to be most often on your input because we want to take that input motor speed, for instance, or combustion engine, gasoline engine speed off of that output or off of that input off of that input angular velocity. And we are then going to slow it down and increase the torque by putting it in combination with a larger sheave. Okay, so the faster sheave is going to be the one that's going to be on the input, and it's going to be the smaller, most often, of the two that are on here. So when we go and we find and we know what our faster shaft is going to be, then we find our RPMs along that vertical axis, and then we have them meet together, and then we're going to pick the size of the V-belt that would be most appropriate to start in our application. And I say that it's a good starting point. Again, based on those two things, we can figure out where are we in the size of our V-belt. We don't want to be too big, but we obviously don't want to be too small either, okay? So that's how we would size our belt. Always best to consult the actual manufacturer's catalog. Again, these are here for our purposes and education. For those same reasons we talked about earlier, you want to use the actual data from that manufacturer. Belt drive geometry. So we've already looked at that sketch 11.5 at the bottom. The belt drive is going to be made up of a minimum of 2 sprockets, and it's going to be a V-belt that is going to ride over those 2 shivs. Then we're going to have them separated by the center distance. That center distance is going to be the center between our input and our output. Or in the case of a belt drive, we call it a driver and a driven shiv, okay? We want to make sure that small center distances that we're kind of in a good range. So we use the equation down at the bottom of my PowerPoint, which is also found on page 304, but it is in the second column. And this is going to give us a nice range for our center distance to land. So for instance, once we size the pitch diameter of each one of our shivs, and we determine that they're commercially available, we take that larger shiv. So when we look here, our ones are going to be our smaller shiv or our driver, and the 2 is going to be our driven or our slower shiv, okay? So for instance, down here on our drive, this would be the driver and this would be the driven. These would be the number 1s and these would be the number 2s, okay? So when we look here at D2, this is going to be the pitch diameter of the larger shiv. Our center distance needs to be larger than that, but smaller than 3 times adding those 2 pitch diameters together. Okay, so somewhere in between there is where our center distance is going to be. We don't want the center distance to be too close because it can cause premature fatigue, okay, or it's going to be real tight belt over the top. We don't want it to be too large because as it rotates, it could cause what we call whip or vibration on that belt excessively. And so then it's going to fail earlier as well. So we want to kind of be in that sweet spot, and that range gets us there, okay? So we always want to be kind of determining once we know what our center distance is, let's compare it to, what the recommended range is going to be. Now, belt length. Belt length is going to be the total length of that belt, okay? So if we look underneath and I look at this V-belt, this V-belt is a continuous loop, okay? There isn't a part here that we would take apart and put back together. It's a continuous length. So what we need to do is we not only need to pick a standard V-belt with standard shivs, but we have to make sure that this length is a standard length in order to incorporate into our design. Okay, so there are going to be standard lengths of belts for each one of these sizes. And those lengths are going to be found here on table 11.2 on page 305. So you'll notice that we have 3 different sections here on this table, one for 3Vs, one for 5Vs, and one for 8Vs. And these are going to be the specific belt lengths that you can get for each one of the sizes, again, that is commercially available. When we are designing, we always want to try, if we can, to incorporate commercially available, readily available parts because they're always going to be less expensive. Number 1, because they're mass produced, and number 2, there's no special tooling that they're creating or customization that they're incorporating. So it's always going to be better for us in the long run cost-wise. Now, to calculate the belt length, okay, we are going to be using equation 11.1. Okay, so capital L is our belt length, and that's the perimeter distance around. So if I would take a tape measure and measure the distance around, that is going to be my belt length. Okay, not just a distance across, it's all the way around. Okay, that's going to be my belt length. Now, to calculate my belt length, the process is a little bit back and forth. We need to first determine where is the center distance or the approximate center distance that we want to be in. In some cases, it might be somewhere in between this range, or if you look at a design and you walk up to something, you might be able to say, I need my center distance to be right at this number, okay, or about this number. Once we have that estimate or that about number, we're going to be putting that in for our center distance C. Then using the pitch diameters of our two shivs that we've chosen, we can calculate that length using this equation, okay? Then what we're going to do is we're going to compare that calculated length to find a belt on this list that is closest to it, whether it's a little bit larger or a little bit smaller, because inevitably you're going to get a length that is not going to be exactly 75 inches long. It's probably going to be 74.2 or something like that. So are you going to go down to 71 or are you going to go up to 75? And you as the designer will kind of make that decision, okay? Then once you pick a standard size belt from this chart, then you're going to go back and you are going to determine the actual center distance, because now this is the center distance based on an actual length of a belt that you are going to be designing into, you know, your application. So that center distance then has kind of a two-phase approach, if you would, kind of to make it easier to calculate. You're first going to calculate B, which is just a generic variable that uses the length and the two pitch diameters. Once we have that value, we're going to plug it in for each of the B values up here to determine the actual center distance, okay? So nothing super complicated, but you just got to, you know, just kind of plug those in. So center distance then will be determined. Now, after we have the center distance determined, we want to make sure that we have an appropriate amount of contact between that belt and that shiv. We don't want to have too much wrap and we don't want to have not enough wrap, okay? If we don't have enough wrap, we don't have enough friction surface to generate or to transmit that torque and force that we're expecting to go through there, okay? So to calculate what the wrap is going to be, the angle of contact or the angle of wrap, theta 1 is going to be on the driver shiv, and theta 2 is going to be the angle of wrap on the driven, okay? At the end, if we look at the next page, the very bottom here, it says belt manufacturers suggest keeping the contact angle greater than 120 degrees, okay, when possible. Now, that is belt manufacturers suggest. You want to know what your specific manufacturer, when you're actually specifying it out in the field, that they require for their design. But you want to just be sure when you calculate your theta 1 and theta 2 for any applications you have for the homework, that it is going to be greater than 120 degrees. Okay. All right. Let's go back to our PowerPoints. So we did angle of contact, center distance, and length. Okay. Velocity ratios and belt speed. Okay. So velocity ratio. Velocity ratio is going to look very familiar to us. Okay. So if we look at the top of page 305 in our second column, velocity ratio is looking at how many times does that driver shiv have to go around to get the driven shiv to go around once. Does that sound familiar? Yeah, absolutely. We did exactly that. We did that comparison when we looked at our previous module on gear design. So kinematically, velocity ratio is calculated the same way. We can use the angular velocities of each one of those shivs. So we can take the driver divided by the driven, or we can physically take the diameter or the dimensions of radius of those shivs, or the diameters, the pitch diameters of the shivs. There's not number of teeth on shivs, so we can't count the number of teeth, all right? But we can use any one of these combinations to determine what that velocity ratio is, okay? And then the other quantity that comes in handy, and that will sound familiar to us, is going to be belt speed. Belt speed is going to be that straight line velocity component as that shiv is rotating around, and it's going to be on the edge or at where the belt actually lies on our shiv. And we're going to calculate that using the radius times the angular velocity or the rotational speed of that sheave. Now, if I know what the pitch diameter is, I simply divide that by 2 and I multiply that by the angular velocity. Remember, in this equation, the angular velocity has to be in what units? Radians per second, exactly. So keep that in mind. Also, in this book, just make sure that your variables here for R1 has to be multiplied by W1. So you have to match up the radius of your sheave to how fast that that particular sheave is going. Okay. Same thing with R2 with W2. Okay. I think they didn't have that quite in there. All right. So I think kind of just going over those basics. Oh, this is a good statement to look at. Belts transfer maximum power at speeds between 4,000 and 5,000 feet per minute. Okay, 4,000 and 5,000 feet per minute. So when we calculate our belt speed, that is a straight line velocity. Okay, and so we want to make sure that our belts are operating in that range. Okay. Let's look at our first example and do this one together. So on page 306, we have example problem 11.1. Okay. Kind of scooch this over. There we go. So we've got a belt drive is being used to transmit power from an electric motor to a compressor for a refrigerated truck. The compressor must still operate when the truck is parked and the engine is not running. The illustration we're going to find is over on the next page here on page 307. So down here is our motor. Oh no, I'm so sorry. That's for our next example. Sorry. I thought there was a figure here, but it's not. That's okay. I was looking ahead. We have a 10 horsepower electric motor that is rated at 3550 RPM. So when we look at our drive, the 3550 RPM is coming in on the driver side, okay? And it has 10 horsepower. The motor sheave is going to be 5 inches in diameter. So that's considered the pitch diameter of that driver sheave coming off of the motor, okay? The compressor sheave, which is the output, is 7.5 inches in diameter. Determine the appropriate industrial belt size, the operating speed of the compressor, and the belt speed. Okay. All right. So first of all, to select the appropriate belt size, that is going to be looking at figure 11.4. And if we look at a figure 11.4, we're going to need to know what the horsepower is of our application and what the faster RPM on the shaft is. Okay. So if we look, we want to find where 10 horsepower is, right? That was listed in our problem. And it told us that we had a motor speed of 3550. So that's up here. It's higher than 3450, but obviously not going to be to 4,000. So we're going to go over and up, and we're going to notice that right about, I don't know, a little bit higher than that. Right about here-ish is where we are going to intersect those two lines. Well, we're well within the zone of a 3V, right? So for the belt size, we would be looking at a 3V belt. So let's start. This is example 11.1. And number 1, belt size equals 3V. And you can say figure 11.4. Okay. So you just read it off of that chart. Okay. Now, if we look back, they also specified a 3V belt based on that figure. Okay. The next thing we need to do, so we've already determined the industrial belt size, we need to determine the operating speed of the compressor, okay? So right now, we know that our W1, which is our driver, is 3550 RPMs, right? We also know the size, the pitch diameter of that sheave. So D1 was equal to 5 inches, right? Additionally, we know that our compressor, the output, which would be D2, is equal to 7.5 inches, right? So the pitch diameters of the driver and the driven are 5 and 7.5, okay? Now, we want to find out what is the operating speed of the compressor, the output, okay? So we want to find out what is W2, okay? So if we go back to previous page here, you'll notice we have equation 11.7. These are the options we have for velocity ratio, okay? So we can set the angular velocities as a ratio to one another, and we have the diameters. So if we can say that W1 over W2 is equal to D2 over D1, we know what W1 is. We know what D2 is. We know what D1 is. We can use it to calculate W2. Agreed? Okay. So we're going to set that up exactly the way we see it there. So we can say W1 over W2, or angular velocity of the driver divided by the angular velocity of the driven. It's going to be equal to D2 over D1. Yes, they flip. Remember, just like with gears, we always want the higher number on top or the larger number on top. When we look at operating speed, that driver coming off the motor is always going to be greater than the driven. But physical size, diameters, the driven is going to be larger than the driver. Okay. So we know 3 of the 4 here, right? So we can calculate or rearrange for W2. I'm going to rearrange first. I like to do that. So I'm going to kind of do my little thing here. And I'm going to say, so you should get D2, you're going to multiply up on the other side. I'm sorry, D1, you're going to multiply up on the other side. D2 is going to come down here, and then W2 is going to go up top. So you should get W2 is equal to W1 times D1 divided by D2. You guys get that same thing? Hope so. I think I did my algebra right. And now we simply want to plug in the values from above. Okay. So this is going to be 3550 RPMs, W1 times D1, 5 inches, divided by D2, 7.5 inches. It's going to be equal to my W2. So inches cancel out. I'm going to end up with RPMs. What do you get for your W2? Should all have our calculators out and plugging it in.
2000.
66.7, right? And that's going to be RPMs, right? So we'll put, and if we peek at our book, they got that same number. They got 2,300. They rounded to 67, but 66.7 is perfect. Okay, good. So that's going to be the operating speed of the compressor. Okay. Now what we want to know is, okay, how fast is that belt moving? Okay. So if we think about it in terms of our kinematic diagram, for instance, I'm going to go like this, number 3. If you remember, if the center of my sheave is going to be the frame, okay, my radius would be going out to here, right? And this would be then the pitch diameter of my sheave. Do you guys see that? Be going all the way around. So my belt speed, for instance, if I'm going in a counterclockwise direction, and we're not told if we're going clockwise or counterclockwise, I'm just picking a direction. My straight line velocity would be out here, right? Perpendicular to that link. This is going to be my belt speed. It's kind of like, you know, the belt is connected here, okay? That's going to be my belt speed. So we know that belt speed is going to be equal to the radius of our driver times the angular velocity of that driver, okay? Now, as we know in this equation, we need our W1 to be in radians per second. But when we talk about belt speed, the most common units are going to be feet per minute. So instead of converting it to radians per second, we're just going to go radians per minute, okay? Because we want this in final belt speed of feet per minute. Does that make sense to everybody? Okay, so it doesn't make sense to go to 2 seconds. So radius, okay, the radius is going to be the diameter divided by 2. So I'm going to say, all right, my radius for my driver is 5 inches, right? So that is going to be 5 inches divided by 2. You can take it divided by 2 and just put 2.5 in there if you wanted to. Okay, so that's my radius. Now my W1, I know my W1 is 3550 RPMs. So I'm going to write that out, 3550 revolutions per minute, okay? Now, I'm going to convert right here. Instead of doing it on the outside and putting that value in, all I'm going to do is I'm going to do my conversion right here. My revolutions are on top here. I'm going to say 1 revolution is equal to 2 pi radians, okay? So my revolutions cancel, and I'm going to be in inches per minute. Do you see that? What do I want my belt speed in, did I say? Feet per minute. So if inches are on top here, I'm going to do one more conversion. I'm going to put inches, 12 inches on the bottom is 1 foot on the top. So now all in one equation, multiply across the top, divide by the bottom, I have feet per minute. Radians magically disappear, right? Okay. So tell me what your belt speed is once you get it.
3,697 feet per minute.
Anybody else get that same number? I didn't get there quite that fast, Nick. You didn't? Okay. I'm just looking, hold on. Oops, 4,000. It looks like 4,647. So try again, Nicholas. You guys use my numbers, right? Yeah, I get the 46, 47 feet per minute. And that's what the book gets as well. Nicholas, make sure, try it one more time.
I see what I did wrong.
You did? Okay, good. Good. So that's how that's how fast our belt is going, okay? Now, this number, as you might remember from the slide, our belts are going to run optimally between 4,000 and 5,000 feet per minute. We are like right in the middle of that range, okay? So this is a good belt speed for our application, okay? Questions on this, because those were the couple of things that they wanted us to do. They wanted us to find the size of the belt, determine what the speed of our output or our compressor was going, and then what that belt speed was going at that rotational speed. Okay. All right. The next problem that we're going to be looking at is going to be 11.2, but we are at just about an hour, and this problem is going to take us a little bit longer. So this would be a great place for us to take our 15-minute break, and then when we get back, we will continue on. So I'm going to stop our recording here.